This limit looks scary. A logarithm raised to an infinite power. But there's a beautiful trick hiding here. Here's our approach. First, we substitute t equals x minus 1 to shift the limit so t approaches 0, placing us right at the critical point x equals 3. Then we use a second-order Taylor expansion of f, exploiting the fact that the first derivative is 0 there. The key move is that the t-squared terms cancel perfectly. When x equals 1, f of 2 plus x equals f of 3, so the ratio inside is exactly 1, and the log is 0. But the exponent blows up. 0 times infinity. This is our indeterminate form, and Taylor is the right tool. We expand f of 3 plus t to second order. Since f prime of 3 is 0, the linear term completely disappears. What survives is f of 3 plus 1/2 times f double prime times t squared, giving us 18 plus 2t squared. The 0 first derivative is the key. Divide by 18 to get 1 plus t squared over 9. The log of that is approximately t squared over 9. Multiply by 18 over t squared, the t squared cancels, and we get exactly 2. Clean, finite, beautiful. The general pattern: whenever the derivative is 0, the quadratic term decides the limit. Here it gives us 2. Option 1 is correct. Two tangent lines to a circle meet at one point. The center sees their touch points at exactly 60 degrees. Where does that meeting point live? Here's our approach. First, we'll rewrite the circle in standard form to find its center and radius. Then, we'll recognize that the 4 points, center, the 2 tangent contacts, and the meeting point, form a kite. The key move is applying 1 trig ratio inside a right triangle. Finally, we'll read off the locus equation directly. Step 1. Complete the square. Grouping the x and y terms, the circle becomes center 2, 3, radius 4. That's our fixed reference point. Every tangent to this circle is perpendicular to the radius at the contact point. That right angle is the engine of this whole problem. Now set up the geometry. From external point P, we draw 2 tangents touching the circle at A and B. Both radii are perpendicular to their tangents, and both tangent lengths from P are equal. So the 4 points form a kite, and in a kite, the main diagonal bisects the top angle. Since the angle at the center is 60 degrees, the kite bisects it to 30 degrees each side. Now look at the right triangle formed by the center, the contact point A, and the meeting point P. We know the angle at the center is 30 degrees, and the radius is 4. Cosine of 30 degrees equals radius over OP. That's root 3 over 2 equals 4 over OP. So OP equals 8 over root 3. Every valid meeting point is exactly this distance from the center. The locus is a circle concentric with the original. Expanding that distance equation and multiplying through by 3 gives us 3 times x squared plus y squared minus 12x minus 18y minus 25 equals 0. That's option 2. The meeting point always traces a circle centered at the same center, just farther out. Look at this integral. X to the 11th power. Absolute value. Trig in the denominator. Looks terrifying, but watch what happens. Here's our approach. First, we'll check whether the denominator is an even function, and it is, because of the absolute value. Then we'll split the numerator into even and odd parts. The odd part vanishes instantly over our symmetric interval. Finally, we evaluate the remaining even integral using a clean substitution and a standard antiderivative. The denominator contains the absolute value of x, which means replacing x with negative x leaves it unchanged. It's even. Now the numerator splits into pi, which is constant and therefore even, plus 4 times x to the 11th, which is odd. Odd divided by even gives odd, and the integral of any odd function over a symmetric interval is exactly 0, so the x to the 11th term disappears entirely. We're left with just the pi over the denominator, an even function. Using the even symmetry doubling property, we rewrite as 2 pi times the integral from 0 to pi sixth. A substitution shifts the argument, so our limits become pi sixth to pi thirds. Now we rationalize. Multiply top and bottom by 1 plus sine. The denominator becomes cosine squared, and the integrand splits into secant squared plus secant times tangent, which is exactly the derivative of tangent plus secant. Evaluating tangent plus secant from pi sixth to pi thirds gives us 2. Multiply by 2 pi, and we get 4 pi. The answer is option 3. A point trapped between two parallel lines, and you need to build an equilateral triangle around it. Here's how. Here's our approach. First, we'll set up coordinates. Put the parallel lines at y equals 0 and y equals 9, and place our point A at height 6. Then we'll let the side BC make angle theta with the lines, which turns the problem into just 2 equations. The key move is summing their squares to find the side length squared directly. One formula gives us the area. The two parallel lines are 9 units apart, 6 from A to L1 plus 3 from A to L2. We place L1 at the bottom, L2 at the top, and our point A at height 6. The horizontal position doesn't matter by symmetry. Now, the side BC runs from L1 to L2, spanning a vertical height of 9. If it makes angle theta with the horizontal, then the vertical component is s times sine theta, which must equal 9. This single constraint links the side length to the angle. We don't need to fix B's horizontal position. In any equilateral triangle, the altitude from a vertex hits the midpoint of the opposite side. The midpoint of BC has height 4.5, right between 0 and 9. Vertex A sits a distance √3/2 times s from this midpoint in the direction perpendicular to BC. Setting A's height to 6 gives us s times cosine theta equals √3. Here's the beautiful part. We have s times sine theta equals 9 and s times cosine theta equals √3. Square both and add. Sine squared plus cosine squared equals 1, so s squared equals 81 plus 3, which is 84. The area of an equilateral triangle is √3/4 times s squared. That's 21 √3. The area is 21 √3 square units. Option 3. The hidden trick was the angle parametrization. It compressed a messy coordinate system into 2 clean equations. 7 observations, 2 unknowns, but mean and variance are enough to pin them both down exactly. Here's our approach. First, we'll use the mean condition to get x plus y. Then the variance condition gives us x squared plus y squared. Those 2 pieces together let us find x and y individually. Once we have them, we substitute into the given set and finish with a slick complementary probability argument. Setting up the mean equation, the 6 known values sum to 42. So, x plus y must equal 14. For variance, we need the sum of all squares. The known squares add to 460. Plugging into the variance formula gives us x squared plus y squared equals 100. 2 clean equations, 2 unknowns. Now here's the key move. We use the identity x plus y all squared equals x squared plus y squared plus twice xy. That gives xy equals 48. So x and y satisfy a simple quadratic. The roots are 8 and 6. Since x is greater than y, x equals 8 and y equals 6. Substituting into the given set, x minus 4 becomes 4 and y becomes 6. So our set is simply 1, 2, 3, 4, 5, 6, 6 consecutive integers. Notice how cleanly the problem was designed to give us this. Now the probability. We want the smaller of 2 chosen numbers to be less than 4. Instead of counting all pairs where this holds, let's use the complement. The complement is both chosen numbers are 4 or more. Only 3 numbers in our set qualify, 4, 5, and 6. We can pick 2 from those 3 in just 3 ways, out of 15 total pairs. So the probability that both are 4 or greater is 3/15, which is 1/5. Therefore, our answer is 1 minus 1/5, which is 4/5. Here's a classic JEE trig question. Find the value of cosecant 10 minus root 3 times secant 10. Here's our approach. First, we rewrite cosecant and secant as fractions and combine them over a common denominator. Then we factor a 2 from the numerator to reveal a compound angle pattern. Next, we apply the sign subtraction identity. Finally, the double angle formula cleans up the denominator, and everything cancels to give a single integer. We start by writing cosecant as 1 over sine and secant as 1 over cosine. Combining over the common denominator sine 10 times cosine 10, the numerator becomes cosine 10 minus root 3 sine 10. One fraction, much easier to work with. Here's the key move. We factor out a 2 from the numerator, leaving 1/2 cosine 10 minus root 3 over 2 sine 10. Now notice that 1/2 is exactly sine 30, and root 3 over 2 is exactly cosine 30. So the bracket matches the sign subtraction pattern. Sine A cosine B minus cosine A sine B equals sine of A minus B. With A equal to 30 and B equal to 10, that's sine of 20 degrees. So the numerator is 2 sine 20. The denominator by the double angle formula is 1/2 sine 20. Now divide. 2 sine 20 over 1/2 sine 20. Sine 20 cancels completely, and we're left with 2 divided by 1/2, which is 4. The trick was recognizing the compound angle pattern hiding in the numerator. 3 vectors, 1 cross product condition, and a constraint that pins everything down. Let's find the answer. Here's our approach. First, we'll write C as a general vector with unknown components x, y, and z. Then we'll expand the cross product as a determinant to get 3 component equations. Next, we'll notice that the system is underdetermined, and use the dot product constraint to fix the free variable. Finally, we add A and C and square the magnitude. Let C equal xi plus yj plus ck. We compute A cross C using the 3×3 determinant. The I component gives 2z minus 2y. The j component gives z plus 2x, and the k component gives negative y minus 2x. We now match these to B. Matching each component to B gives us 3 equations. From the I component, z minus y equals 4. From j, z plus 2x equals 7. From k, y plus 2x equals 3. Substituting the second and third into the first gives a trivial identity. 4 equals 4. This means the system has a free parameter. That's because A and B are perpendicular. You can verify their dot product is 0. So the cross product alone can't uniquely determine C. We express y and z in terms of x. Y equals 3 minus 2x. Z equals 7 minus 2x. Now we apply the constraint. X plus y plus z equals 4. Substituting our expressions gives 10 minus 3x equals 4. So x equals 2. Back substituting, y equals negative 1 and z equals 3. Our vector C is 2i minus j plus 3k. Adding A and C, the I components give 1, the j components give 1, and the k components give 5. So A plus C equals I plus j plus 5k. The squared magnitude is 1 plus 1 plus 25, which equals 27. The answer is option 4, 27. When A cross C equals B, always check if A and B are perpendicular first. 2 conics, 1 shared secret, their foci. And from that single link, we unlock the hyperbola completely. Here's our approach. First, we'll extract the foci from the given ellipse using the standard focal distance formula. Then, we transfer those foci directly to the hyperbola. Next, we use the given eccentricity to find the semi-transverse axis. Finally, we compute the latest rectum in one clean step. The ellipse is x squared over 36 plus y squared over 16 equals 1. Here, a squared is 36 and b squared is 16. Since a is greater than b, the foci lie on the x-axis. The focal distance formula gives c squared equals 36 minus 16, which is 20. So c equals 2 times the square root of 5. Now, since the hyperbola shares these foci, its focal distance is also 2 times the square root of 5. Eccentricity equals c over a, and we're told eccentricity is 5. So, the semi-transverse axis A equals 2 times the square root of 5 over 5. That's a small value, which makes sense because a very large eccentricity means a wide-open hyperbola. For a hyperbola, b squared equals c squared minus a squared. Notice this is the opposite sign from the ellipse. Here, that gives 20 minus 4/5, which equals 96 over 5. Now, the latus rectum is simply 2 times b squared over a. Substituting our values, 2 times 96 over 5, divided by 2 root 5 over 5. The 5's cancel beautifully, and we get 96 over root 5. That's option 4. The answer is 96 over root 5. The key insight here, once you know the foci and the eccentricity, the hyperbola is completely determined. Foci give you c, eccentricity gives you a, and everything else follows in a straight line. Here's a sum of 25 fourth power terms. It looks intimidating, but there's a hidden period 3 cycle that collapses the entire problem into just 2 cases. Here's our approach. First, we'll recognize that x squared plus x plus 1 equals 0 means x is a cube root of unity. Then we'll use the fact that x cubed equals 1 to evaluate each bracket by its residue mod 3. The key move is realizing that every bracket equals either 2 or -1. We count how many terms fall in each case and multiply. The equation x squared plus x plus 1 equals 0 is the cube root of unity equation. Its roots are the primitive cube roots of unity. Call them omega and omega squared. The defining properties are omega cubed equals 1 and omega plus omega squared equals -1. This period 3 structure is everything. Since x is omega, the inverse of x is x squared, because x times x squared equals x cubed equals 1. So, x to the n plus x to the minus n equals omega to the n plus omega to the 2n. Now, because omega cubed equals 1, this repeats with period 3. When n is divisible by 3, omega to the n equals 1, so the bracket equals 2. When n is not divisible by 3, we get omega plus omega squared, which equals -1. Now we raise to the 4th power. 2 to the 4th is 16. -1 to the 4th is also 1. So each of the 25 terms is either 16 or 1. Nothing else. The final count. From 1 to 25, there are exactly 8 multiples of 3. 3, 6, 9, all the way to 24. The remaining 17 terms are the non-multiples. So our sum is 8 times 16, which is 128, plus 17 times 1, giving us 128 plus 17, which equals 145. The answer is option 1, 145. Whenever you see x squared plus x plus 1 equals 0 in a JEE problem, write omega cubed equals 1 immediately. The period 3 cycle does the rest. Here's a classic JEE 3D geometry question. Find where a perpendicular from a point lands on a line, then project that landing point onto another vector. Here's our approach. First, we'll parameterize any point on the given line using lambda. Then we'll form the vector from our external point to this general foot, and set its dot product with the line direction to 0. That's the perpendicularity condition. Solving gives us lambda equals 1, which pins down the exact foot. Finally, we apply the scalar projection formula. The line passes through -1, 3, 1 with direction vector 2, 3, -1. Any point on the line is -1 plus 2 lambda, 3 plus 3 lambda, 1 minus lambda. We call this our candidate foot F. Now we form vector AF from the given point 5, 4, 2 to this general F. For F to be the true foot, AF must be perpendicular to the line's direction. Setting the dot product to 0 gives -14 plus 14 lambda equals 0, so lambda equals 1. Plugging lambda equals 1 back in, alpha equals 1, beta equals 6, gamma equals 0. Let's double check. The dot product of AF with the direction is -8 plus 6 plus 2, which is 0. Confirmed. Now the key move. The scalar projection of the position vector 1, 6, 0 onto 6, 2, 3 equals their dot product divided by the magnitude of the second vector. The dot product is 6 plus 12 plus 0, which is 18. The magnitude of 6, 2, 3 is root of 36 plus 4 plus 9. That's root 49, which is 7. So the projection is 18 over 7. The answer is option 2, 18 sevenths. Notice how the vector 6, 2, 3 was specifically chosen, so its magnitude equals exactly 7, giving a clean fraction. That elegant denominator is the JEE signature on this problem.
Two inverse trig functions, one with a rational expression, one with a quadratic. The question asks, where is this function even defined? The domain is a hidden interval, and alpha plus 2 beta is the prize. Here's our approach. First, we'll find where the arc cosine input stays between -1 and 1. That means solving two rational inequalities using sign diagrams. Then, we'll find where the arc sine input stays in the same range. The lower bound is always satisfied.
So we only need the upper bound, which gives a clean quadratic factoring. The key move is intersecting both conditions on the number line. Finally, we read off alpha and beta and compute the answer. For the arc cosine part, we split the condition into two inequalities. The lower bound rearranges to the fraction 6 minus x over 11 minus 3x being non-negative. A sign diagram at x equals 11 thirds and x equals 6 shows this holds for x less than 11 thirds, or x at least 6. The upper bound rearranges to 5x minus 16 over 11 minus 3x being non-positive. Sign analysis at x equals 3.2 and 11 thirds gives us x at most 16 fifths, or x greater than 11 thirds. Intersecting both pieces, the arc cosine condition becomes x at most 16 fifths, or x at least 6. Now for the arc sine. The argument is a quadratic. 2x squared minus 3x plus 1. The discriminant is negative, so this quadratic is always above -1. No restriction there. For the upper bound, we need x times 2x minus 3 to be at most 0, which gives 0 to 3 halves. Here's the key insight. The interval 0 to 3 halves lies entirely within x at most 3.2. So the intersection is simply the interval from 0 to 3 halves. That gives us our answer. Here's a parabola problem with a hidden second parabola inside it, and that's the key. Here's our approach. We have the parabola x squared equals 4y, with vertex O at the origin. Point Q moves along it. A new point P always divides segment OQ in the ratio 2 to 3. First, we'll find the locus of P using the section formula. Then we'll find the chord of that new conic with midpoint 1, 2. The key move is recognizing that this ratio creates a simple scaling transformation. Let's parameterize. Any point Q on the parabola can be written as 2t, t squared. Now we apply the section formula. Since P divides OQ in ratio 2 to 3 from the origin, P lands at 4t over 5 in x and 2t squared over 5 in y. Notice how the origin being at O makes this just a 2/5 scaling of Q's coordinates. Now we eliminate the parameter. T equals 5, x over 4. Substitute into the y coordinate, and we get y equals 5x squared over 8. That's conic C, a new parabola, narrower than the original, but with the same vertex at the origin. For the chord of C bisected at 1, 2, let the two endpoints have x-coordinates S1 and S2. The midpoint condition forces S1 plus S2 to equal 2. The slope of the chord simplifies beautifully. It's 5 times the sum of the parameters divided by 8. With sum equal 2, slope equals 5 over 4. Plugging into point-slope form through 1, 2 gives us 5x minus 4y plus 3 equals 0. That's option 1. Clean, elegant, done. The takeaway: whenever a point divides a segment from the origin in a fixed ratio, think scaling. The locus is always a similar conic, just rescaled. A differential equation with an arctangent twist and a clean initial condition. We need to find y of 1. Here's our approach. First, we'll rearrange into standard linear ODE form. Then we'll compute the integrating factor, which turns out to be e raised to arctangent x. We multiply through, spot a perfect derivative on the left, and integrate both sides. The right side integral needs integration by parts. Finally, we apply the initial condition to find the constant, and evaluate at x equals 1. Rearranging the equation, we get dy over dx plus y over 1 plus x squared equals arctangent x over 1 plus x squared. This is the standard linear form because the coefficient of y, which is 1 over 1 plus x squared, integrates cleanly to arctangent x. The integrating factor is e to the arctangent x. When we multiply the ODE by this factor, the left side becomes the exact derivative of y times e to the arctangent x. So, integrating both sides is now straightforward. The right side integral, e to t times t, is solved by parts. With u equals t and dv equals e to t, we get e to t times the quantity t minus 1 plus a constant. Substituting back, the general solution is y equals arctangent x minus 1 plus c times e to the negative arctangent x. Plugging in y of 0 equals 1. Since arctangent of 0 is 0, we get 1 equals negative 1 plus c. So c equals 2. At x equals 1, arctangent of 1 is pi over 4. So y of 1 equals 2 over e to the pi over 4 plus pi over 4 minus 1. An equation that looks like a simple quadratic, but it secretly has 4 roots. Let's find them all. Here's our approach. First, we'll substitute u equals x minus 1 to collapse both terms into a single variable. Then we'll split into 2 cases based on whether u is positive or negative. Each case gives 2 roots, and finally we sum all 4. Notice that both the squared term and the absolute value involve the same expression, x minus 1. So we let u equal x minus 1. The equation becomes u squared minus 5 times the absolute value of u plus 6 equals 0. A W-shaped curve, symmetric about 0. When u is non-negative, the absolute value is just u itself. The equation becomes u squared minus 5u plus 6, which factors as u minus 2 times u minus 3. So u equals 2 or 3, giving us x equals 3 and x equals 4. When u is negative, the absolute value flips the sign. We get u squared plus 5u plus 6, which factors as u plus 2 times u plus 3. So u equals negative 2 or negative 3, giving x equals negative 1 and x equals negative 2. Here's the key insight. The W shape is symmetric, so positive and negative u roots cancel out. The u sum is 0. Since x equals u plus 1, with 4 roots we add 4, giving a total sum of 4. 3 plus 4 minus 1 minus 2. The sum of all roots is 4. How many relations can you define on a 4-element set that are both reflexive and symmetric at the same time? This is a classic JEE question, testing your understanding of relation properties and combinatorial counting. Here's our approach. First, we identify what the reflexive condition forces. Every element must relate to itself, locking in the diagonal entries. Then we apply the symmetric condition, which forces off-diagonal entries to come in matching pairs. The key move is recognizing that each of those 6 symmetric pairs is an independent binary choice, include or exclude. Finally, we multiply those independent choices to get the total count. A relation is reflexive if every element is related to itself. For our 4-element set, the pairs AA, BB, CC, and DD must all be in the relation. These 4 diagonal pairs are completely fixed, 0 choice here. Think of them as the locked diagonal of a 4x4 grid. Symmetric means if A, B is in the relation, then B, A must also be there. In our 4x4 grid, there are 12 off-diagonal cells. These naturally form 6 symmetric pairs. For each pair, we have exactly 2 options, Include both entries in the relation or exclude both. We cannot include just one, since that would break symmetry. Here's the key insight. All 6 symmetric pairs are completely independent of one another. Whether we include the AB pair has no effect on whether we include the AC pair. So we have 2 choices for each of the 6 pairs. 6 independent binary decisions. Multiply them together. 2 to the power of 6 equals 64. That's the total number of relations on a 4-element set that are both reflexive and symmetric. Option 1, 64, is correct. Remember this pattern. For any n-element set, the answer is always 2 to the power of the combination of n taken 2 at a time. 3 unknowns, 3 hidden conditions, and 1 answer hiding in plain sight. Let's crack it. Here's our approach. First, we'll pull out exactly 4 coefficients from the binomial expansion of 1 minus 2x raised to the 26th power. Then we'll set up 3 equations, one for each coefficient condition. The key move is eliminating variables cleanly. Finally, back substitution gives us all 3 unknowns, and we sum them up. The binomial theorem tells us the coefficient of x to the r in 1 minus 2x to the 26 is c of 26 choose r times negative 2 to the r. We need r equals 0 through 3. That gives us 1, negative 52, 1300, and negative 20,800. These 4 numbers are the building blocks of everything that follows. Now let's build the 3 equations. For the coefficient of x to be negative 56, the terms that contribute are b times the x0 coefficient plus c times the x1 coefficient, giving us b minus 52c equals negative 56. For x squared equals 0, all 3 terms contribute. A minus 52b plus 1300c equals 0. For x cubed equals 0, we get negative 52a plus 1300b minus 2800c equals 0. Here's the key insight. Divide the third equation by negative 52. It becomes a minus 25b plus 400c equals 0. Subtract this from the second equation, and a cancels out completely. We get b equals 100 thirds times c. Since b must be an integer, c has to be 3. That pins b to 100. Plugging back into the first equation confirms it. Negative 56 checks out. Finally, substitute b equals 100 and c equals 3 into the second equation. A equals 52 times 100 minus 1300 times 3, which simplifies to 5200 minus 3900, giving us a equals 1300. So a plus b plus c equals 1300 plus 100 plus 3, which is 1403. Here's a beautiful area question from JEE Maths 2026. We need to find the area inside an ellipse, but outside a region formed by 2 absolute value curves. Here's our approach. First, we'll rewrite the ellipse in standard form and read off its area using the formula pi times a times b. Then, we'll figure out exactly what region those 2 V-shaped curves bound together. Spoiler, it's a diamond. The key move is checking that the diamond fits entirely inside the ellipse. Finally, we just subtract. The ellipse is x squared over 4 plus y squared equals 1. That means a equals 2 and b equals 1. So the total ellipse area is pi times 2 times 1, which gives us 2 pi. That's our starting number. Now for the 2 curves. The upward v has its lowest point at 0, negative 1, and the inverted v peaks at 0, 1. They intersect where the absolute value of x equals 1, giving us the points 1, 0 and negative 1, 0. Together, these 4 vertices, top, bottom, left, right, form a diamond with all 4 sides equal. The diamond's diagonals run from negative 1 to 1 horizontally and from negative 1 to 1 vertically, each with length 2. Area of a rhombus equals half the product of its diagonals. So diamond area equals 2. The diamond's top vertex at 0, 1 sits exactly on the ellipse. Check. 0 over 4 plus 1 equals 1. Same at the bottom. The left and right vertices are strictly inside. Every boundary point of the diamond stays inside or on the ellipse. so the entire diamond is contained. That means the required area is simply ellipse area minus diamond area, 2 pi minus 2. We factor out 2 to get 2 times the quantity pi minus 1. That's option 3, and our answer. The key takeaway: when you see two absolute value V-curves like this, recognize the diamond shape immediately and check containment before reaching for integration. Geometry beats calculus every time here. Here's a JEE problem that hides a clever connection between vectors and circles, and the key insight unlocks everything. Here's our approach. First, we'll use a cross-product identity to show that C plus D must be parallel to the fixed vector 2i, 3j, 4k. Then the magnitude condition pins down exactly two possibilities. We compute the dot products to get lambda 1 and lambda 2. Finally, we apply the two conditions for a circle to find k. The given cross-product equation is symmetric about the vector b. Here's the key move. Cross products are anti-commutative, so b cross d equals negative d cross b. Bringing everything to one side gives c plus d all crossed with b equals 0. A zero cross product means the two vectors are parallel, so c plus d must point along b. Since c plus d equals t times b, we use the magnitude constraint. The magnitude of b is root 29, same as the given magnitude. So, t equals plus or minus 1. Two cases. Now we take the dot product with negative 7i plus 2j plus 3k for each case. When t equals 1, the dot product comes out to 4. When t equals minus 1, it flips to minus 4. So lambda 1 is 4 and lambda 2 is minus 4. Plugging in, the conic equation has k squared as the x squared coefficient and 3k minus 2 as the y squared coefficient. For a circle, these must be equal. That gives k equals 1 or k equals 2. The cross-term coefficient must also be 0. That gives k equals 1 or k equals 4. The only value satisfying both conditions is k equals 1. For k equals 1, the equation simplifies to x squared plus y squared minus 8x plus 12y minus 4 equals 0. A genuine circle centered at 4, negative 6. 6 inputs, 9 outputs, strictly increasing, and none allowed to equal their own index. How many survive? Here's our approach. First, we'll recognize that a strictly increasing function is just a 6-element subset of 9 values. That collapses the problem instantly. Then we'll spot a hidden forced inequality that simplifies the constraint. The key move is a substitution that converts everything into a clean stars and bars count. Finally, we read off the answer. A strictly increasing function from 6 elements to 9 is completely determined by which 6 values we pick. Arrange them in order, assign smallest to f of 1, next to f of 2, and so on. So we're really counting 6-element subsets of 1 through 9. Now here's the hidden insight. Because f is strictly increasing, f of 1 is at least 1, f of 2 is at least 2, and in general, f of I is always at least I. So the condition f of I not equal to I simply becomes f of I strictly greater than I. Here's the key move. Define u sub I as f of I minus I minus 1. This quantity is non-negative, non-decreasing across all 6 positions, and capped at 2, because f of 6 can be at most 9. So we need non-decreasing sequences of length 6 from the set 0, 1, 2. Counting non-decreasing sequences of length 6 from 3 values is exactly stars and bars. C of 8 choose 2, which equals 28. That's our answer. Option 4. The takeaway: whenever you see strictly increasing between consecutive integer sets, that structure secretly forces f of I at least I. So no fixed point just means shift every value up by 1. A geometric progression is hiding a clever shortcut worth knowing. Here's our approach. First, we'll use the product condition. 3 consecutive GP terms multiplied together give the middle term cubed. That immediately hands us the value of a sub 3. Then we'll substitute into the sum condition to build a quadratic in R squared. Finally, a ratio trick gives us the answer in one multiplication, in a GP with first term A and common ratio R. Consecutive terms scale by R each step. So A sub 2, A sub 3, and A sub 4 are A times R squared, and A times R cubed. Their product equals A sub 3 cubed. The R factors cancel symmetrically. Since A sub 3 cubed equals 64, A sub 3 equals 4. This single value is the anchor. We can now express the first term A as 4 over R squared. Now we use the sum condition. The terms A sub 1, A sub 3, and A sub 5 form a sub-GP with ratio R squared. After substituting A equals 4 over R squared and multiplying through, we arrive at the quadratic. 28t squared minus 785t plus 28 equals 0, where t is R squared. The discriminant simplifies beautifully. 785 squared minus 4 times 28 squared equals 783 squared. So we get t equals 28, or t equals 1 over 28. Since the GP is increasing, R must be greater than 1, so R squared equals 28. Here's the elegant insight. Notice that A sub 3 plus A sub 5 plus A sub 7 equals R squared times the quantity A sub 1 plus A sub 3 plus A sub 5. So the answer is simply 28 times 813 over 7. That's 4 times 813, which gives us exactly 3252. The ratio multiplier trick is what makes this problem fast. Option 4, 3252, is correct. A sequence where each term is half the previous, with a mysterious correction term. What does that correction encode? Here's our approach. First, we recognize this as a first-order linear recurrence, separable into a particular solution and a homogeneous part. Then, we test whether 2 over n squared is the particular solution. The question itself is hinting at this. Next, we apply the initial condition to pin down the constant. The sum collapses into a standard geometric series. Let's set up the structure. The recurrence says each new term is half the previous plus a forcing function. The homogeneous equation has general solution a times 1/2 to the n minus 1. Now the key move. Let's test whether 2 over n squared satisfies the recurrence. We substitute it in, multiply through by n squared times n plus 1 squared, and compare coefficients. The n squared term gives c equals 2. The linear term gives c equals 2. The constant term gives c equals 2. All three agree, so 2 over n squared is our particular solution. The general solution is 2 over n squared plus a times 1/2 to the n minus 1. Applying a1 equals 1 gives us a equals -1. So an minus 2 over n squared equals -1/2 to the n minus 1. A geometric sequence. The infinite sum has first term 1 and ratio 1/2, giving -2. Taking the absolute value, our final answer is 2. Two matrices, A and B. Each satisfies a quadratic equation. That equation is hiding the answer, if you know where to look. Here's our approach. First, we'll use the polynomial conditions to read off the trace and determinant of each matrix directly. That instantly gives us alpha and beta. Then, we'll use a substitution trick to compute the cubes of A and B without tedious matrix multiplication. Finally, we'll apply one key determinant formula to reach the answer. When a 2 by 2 matrix satisfies a quadratic equation like a squared minus 4a plus 2i equals 0, that polynomial is precisely its characteristic equation. So the trace of a is 4, making alpha equal to 2. The same reasoning applies to b. Its trace is 3, giving beta equal to 2. Now here's the key move. Since a squared equals 4a minus 2i, we can express a cubed as 14a minus 8i. One substitution, no matrix multiplication. Since b squared equals 3b minus I, we get b cubed as 8b minus 3i. Both cubes are just linear combinations of their base matrices. Subtracting gives us a cubed minus b cubed equals the matrix 15, 20, 6, 7. Its determinant is 15 times 7 minus 20 times 6. That's 105 minus 120, which equals negative 15. Here's a crucial identity for any 2 by 2 matrix. The determinant of its adjugate equals the determinant of m raised to the power n minus 1. Since n equals 2, that's just negative 15. Squaring gives us negative 15 squared, which is 225. That's our answer, 225. Notice how the structure of the problem made each step almost mechanical once you saw the eigenvalue connection. An absolute value integral with 3 sine terms. Looks intimidating, but one factoring move turns this into a problem you can crack in 2 minutes. Here's our approach. First, we'll use the sum to product identity to factor sine of 3x plus sine of x into a clean product. Then we'll find the 2 points on 0 to pi where the expression changes sign. Next, we'll split the integral into 3 pieces across those points. Finally, one antiderivative evaluates all 3 pieces, and the factor of 6 cancels perfectly. Step 1. Factor. Notice that sine 3x and sine x are a symmetric pair separated by 2x. The sum to product identity collapses them. Sine 3x plus sine x equals 2 sine 2x cosine x. Adding the middle term sine 2x gives us sine 2x times the quantity 2 cosine x plus 1. 3 messy terms become a clean product. Step 2. Find the sign changes. Sine 2x flips from positive to negative at x equals pi over 2. The second factor, 2 cosine x plus 1, becomes 0 at x equals 2 pi over 3. So the product is negative only on the short interval between these 2 points. Everywhere else, it's positive. Step 3. Integrate each piece. The antiderivative of our expression works out to negative 4 cosine cubed x over 3 minus cosine 2x over 2. We evaluate this at 4 boundary points, 0, pi over 2, 2 pi over 3, and pi. The 3 pieces give us 7/3, 1/12, and 5/12. Adding them yields 34 over 12, which is 17/6. Multiply by the factor of 6 outside the integral, and it cancels the 6 in the denominator exactly. The answer is the clean integer, 17. This looks like a counting problem, but hidden inside is a beautiful pattern from modular arithmetic. Here's our approach. First, we'll analyze what 6 to the power m and 9 to the power n give modulo 5. Then we'll find exactly when their sum is divisible by 5, which gives us p. Next, we'll hunt for prime squares in the valid range, count diagonal lattice pairs, and get q. Finally, we add them for the answer. Let's tackle the first term. Since 6 equals 5 plus 1, it's congruent to 1 modulo 5. That means 6 to the m is always 1 modulo 5 for any value of m. The first term is completely constant. It never changes. That's the key insight. Now for 9 modulo 5. Since 9 equals 10 minus 1, 9 is congruent to negative 1 modulo 5. So 9 to the n alternates. When n is odd, it gives 4 modulo 5. When n is even, it gives 1. For the whole sum to be divisible by 5, we need 1 plus 4 equals 5, which happens only when n is odd. With m free over all 50 values and exactly 25 odd values of n, p equals 50 times 25. That's 1250. For q, we need m plus n to equal the square of a prime. Since both m and n range from 1 to 50, their sum goes from 2 up to 100. The prime squares in that window are 4, 9, 25, and 49, from primes 2, 3, 5, and 7. Counting the valid pairs along each diagonal gives 3, 8, 24, and 48. So q equals 83. Adding it all up, 1250 plus 83 gives us P plus Q equals 1333. What if a quadratic in M has equal roots for every single value of x? That's our hook. Here's our approach. First, we'll use the equal roots condition to get a key relation between f, its first derivative, and its second derivative. Then, we'll recognize that this forces f to be an exponential. We pin down the exact exponential using the initial values. Finally, we compose it with log x minus x and find where that's increasing. The quadratic has equal roots, so its discriminant must be 0. Setting that up gives us 4 times f prime squared minus 4 times f double prime equals 0. Simplifying, the square of f prime equals f times f double prime. This single relation must hold for every x in the real line. Here's the key insight. Let's define g of x as the natural log of f of x. Then g double prime works out to exactly the numerator we just found, which is 0. So g is linear, g of x equals ax plus b. Exponentiating, f of x equals c times e to the ax. Now we plug in, f of 0 equals 1 forces c to equal 1. F prime of 0 equals 2 forces a to equal 2. So our function is f of x equals e to the 2x. Let's compose. We substitute log x minus x into f. Since f of u equals e to the 2u, we get x squared times e to the negative 2x. Notice the domain is x greater than 0. Differentiating h with the product rule gives 2x times e to the negative 2x times 1 minus x. Since the exponential and 2x are always positive, the sign depends entirely on 1 minus x. So h is increasing precisely when x is between 0 and 1. The largest interval is the open interval from 0 to 1. Alpha plus beta equals 0 plus 1, giving us the answer, 1.